So we'll see. We'll simply take a simple design like D flip flop design, and we will see how to use this synchronous reset, asynchronous reset, and how to generate a clock and how to write a test bench, everything. Okay. Yeah. 1 minute. It's getting loaded. I'm using 23 version. So let's see how to write the design first. The D flip flop design. So let me zoom in somewhat so that yeah. So module D underscore flip flop. So clock comma reset comma D underscore in comma. So these are our inputs, right? So input clock comma reset comma D underscore in, and output reg q comma q bar. Okay. So these are my inputs and outputs of my design. Okay. Input clock comma reset comma D underscore in comma output reg q comma q bar. Okay. So always at the rate passage of clock, my design should work. Begin. If reset my queue, should I use non-blocking or blocking? So should I use blocking or non-blocking for this particular design? Non-blocking.
Blocking, sir.
Blocking or non-blocking? Okay.
Non-blocking.
Okay. We should use non-blocking. So the reason also we have discussed in that particular session, right? So where we have discussed what is happening if we use blocking assignments and what is happening if we use non-blocking assignments, how the design will work if we use blocking assignments, and how the design is going to work if we use non-blocking assignments. I think that recording is not available due to some issues. Okay, so we will plan one more session discussing again regarding this particular blocking and non-blocking assignments. Okay, so no issues. So for sequential circuits, we prefer non-blocking assignments, and for combinational circuits, we use blocking assignments. The reasons we have discussed in that session previously, but due to some technical issues that particular recording was audio was not recorded. Okay, no issue. So we will use here non-blocking assignment, and we are going to make it as 0 if we use the reset, and begin. Q is equal to 0 and q bar is equal to 1. Okay, since q bar is not of q, it is going to be complement of q. Else if my d underscore in, that is d underscore in is equal to 1, begin. My q is equal to d underscore in, and q bar is equal to not of d underscore in. Okay, and I'm ending this always block, and I'm ending the module. Okay, in Verilog there is no need to mention explicitly as d in underscore equal to 1. Okay, so there is no need to mention, just we can write simply d underscore in, that's it. Okay, and we'll write in module. So is it clear? The design code, is it clear for everyone? Can we move forward? So this is the design code for our
Yes, sir.
D flip flop. Okay, so is it clear for everyone? Yes, can we move forward? Yes. Now,
Yes, yes, sir.
yes. Yeah. Now let us see how to write the test bench for this particular sequential circuits. So let me create one file for my test bench. Simulation source. Next, create file dff underscore tv. Okay, finish dff underscore tb. Yes. Let me open this file, dff underscore tb. Yes. Now, in this dff underscore tb, so when we are going to write our test bench, we have seen some set of rules. So what is the first step we should follow? Step 1 is declaring our input ports, that is inputs and outputs. Okay, so declaring the data types for input and output variables. Okay, so this is step 1. That is, we are going to declare uh, clock and d underscore in and reset as reg, and our outputs q and q bar as well. Okay, so this is the first step we are going to follow. Is it clear? In the input should be reg and output as well. Yes, so inputs we have declared as reg and output as well. Okay, so if you recall that particular diagram which we have seen in our early sessions. Okay, now next is step 2 is instantiation. So how we are going to instantiate? So we are going to write our module name, which is nothing but d underscore flip flop. So it is our step 2, d underscore flip flop, and the instance name dut. Okay, so I'm following connection by order. So I will simply going to write clock comma reset comma d underscore in comma q bar. Okay, so this is my step 2, clock comma reset comma d in q bar. So this is my step 2. Now, so in the case of combinational circuits, we have just simply driven our inputs. Okay, in the case of combinational circuits, while we are developing the test bench, we have just simply driven the input variables. Okay, but in the case of sequential circuits, we are going to generate a clock also. Okay, so that is our step 3, that is generation of clock. So how we are going to generate a clock? What we are going to do? Can anyone answer? So how can we generate a clock? How we are going to generate a clock? Using delay. Okay, which loop, which type of construct we can use for generating this particular clock? Always, yes. Or you can use forever also. Okay, you can use always or you can use forever. So I'm going to use this particular always. Now before that, we should initialize the clock. Okay, since it is a reg variable, so we are going to initialize the value of clock. So I will write it here, initialization of input variables. That is our clock, d in, and reset everything. Okay, begin clock is equal to 0 and reset, which is also equal to 0, d underscore in is also equal to 0, end. Okay, and always hash phi clock is equal to not of clock. So what is the time period here? Can anyone answer? What may be the time period of this particular clock? Always hash
5 bit.
10. Okay, so for 5 time units this particular clock will be equal to 0, and another 5 time units the clock will be equal to 1. Okay, for first 5 time units it will be equal to 0, and another 5 time units it will be equal to 1. So this step is nothing but your generation of clock. Generation of clock. Okay, so for first 5 time units it will be equal to 0, and for another 5 time units it will be equal to 1. Okay, now Next is driving the stimulus. Okay, so within an initial begin and block, what we can do, we can apply reset signal. So when we should apply this reset signal, so whether we should apply it at positive edge or whether we should apply at negative edge.
Negative range.
Okay, others, when we should apply this reset signal, we should apply it at positive edge or whether we should apply it at negative edge. Okay. So in HTA we have a concept of setup time and hold time. Okay. So once please revisit those concepts of setup time and hold time. So to our setup time and hold time condition, to avoid the setup time condition, so we are going to apply the reset at negative edge. So at the rate neg edge of clock, reset is equal to 1. I am applying the reset signal, and at the rate neg edge of clock, I'm deassetting the reset signal. So when you are simulating it, the setup time and hold time violations, nothing will be happen because tool will be taking care of that. But in a good practice, when you are developing some test bench, you should follow the particular conditions, all the setup time and hold time conditions, keeping in mind. So negate of clock, I will apply my D in signal, which is equal to 1, and at another negate of clock, what I will do, simply I will make it as 0, and I will monitor my uh, I will monitor my Q and Q bar. The values of Q and Q bar are percentage D, comma Q bar. So this is how I am monitoring them. And end module. End module is, I think it is already written. Yes. So this is how we are going to write a test bench for any sequential circuit. Same procedure for all the sequential circuits. What is the first step? First we should declare the inputs and outputs. Next is instantiation, followed by initialization, and next is generation of clock, followed by driving the data or the stimulus. That's it. This is the test bench for any sequential circuit. So is it clear for everyone? Can we move forward?
Yes, sir.
Yes. So let me set a stop so that it will be simulated. Run behavioral simulation. Yes. So till then it is getting simulated. We're also planning one course on after completing this Verilog. My next plans are starting a course on FPGA. Like we have learned everything on simulated oriented way, right? So I'm planning to launch a course on implementing the things we have learned on FPGA, like developing some simple projects like ALU and how to do the hardware synthesis, everything gate level netlist. I'm planning such type of courses. Okay, let's see whether it will happen or not. Okay. So this is my clock signal, which is having a time period of 10 nanoseconds, and this is my input signal. So which is applied. So before that, we have applied our reset signal. So initially, my Q and Q bar are unknown. So if I apply the reset signal before at the negate of clock, I've applied my reset signal at negate of clock. So my reset signal will be active only at the positive edge of the clock. So then only my Q will be equal to 0 and Q bar will be equal to 1. Next, I am applying my input at negate of clock, and it will be sampled in the positive edge of the clock. And since D is equal to 1, my Q is equal to 1 and Q bar is equal to 0. Okay. and since my din is equal to 0 in the next clock edge, my output will be equal to 0. Here why output is not happening? Okay, sorry. So why it's not happening? What is the error we have? Can anyone debug it? My input din is equal to 0, but my output is not going to 0, not desetting to 0. Can anyone tell me the reason why it is not happening? Okay, I will show you the code. So this is the code. So I already got the mistake. What is happening? Can anyone try?
Sir, that else if condition is creating the problem. I think when Dean is equal to 1, then it executes.
Hmm. Okay.
So we should remove, I think, else if, in place of else if, we should only have else.
Okay. So if we write else, okay, that is also uh, we can know, or simply we can write another else condition, and we can write q is equal to uh, d underscore in, like that also we can write. Okay, we can do both of the things. Okay, yes. Let me relaunch this again. So is it happening now? D in is equal to 0, my q is equal to 0, and again D in is equal to 0, my q is equal to 0, and q bar is equal to 1. Yes. So is it clear how to write a test bench for a sequential circuit? Is it clear for everyone? Yes. Others, is it clear? We cannot use the symbol not. We cannot write the keyword not. If you want to use the operator for not, I will show you. You can use exclamatory operator or this operator. This symbol is for not. You cannot write not. Okay, this is not present. Yeah. So others, is it clear? Only I got few responses. Yes. So please try writing the code for ripple carry adder, both the design. No. So the design, what we have done now, is it a synchronous circuit or asynchronous circuit? Is it synchronous reset signal or asynchronous reset signal? The code which we have written now, whether the reset signal, is it synchronous or asynchronous? Synchronous. Okay. So I think you can write the code for asynchronous reset. So in our previous sessions, while we were discussing somewhere we have discussed asynchronous reset, how to write the code for asynchronous. Can anyone remember that? We have drawn some waveforms and we have discussed what is meant by synchronous reset, asynchronous reset. Also we have discussed. Can anyone remember? Yes or no? No means I will discuss now. Okay. So, okay. So if you remember, we have already discussed how to write the code for synchronous reset and asynchronous reset. So okay, no issue, we will discuss it now. Or yeah, once go through the previous recordings, you can find it out and figure out how to write the code for asynchronous reset. Okay, so I remember strongly that I have discussed this asynchronous and asynchronous, and I've also drawn the waveforms like we have discussed detail in